The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
All right. Thank you very much. It's a pleasure to be here. I'm going to talk about a couple of things today. I'm going to talk about some of my research, and I'm also going to talk about an activity I spent 2 years in industry helping to start a new UAV program at Google. But before I get into that, I just want to sort of set some expectations and some understanding of where the world is in terms of UAVs. About 10 years ago, when I started at MIT, most people thought about UAVs and drones, to the extent they ever thought of them at all, as big military assets. And in fact, if you go to Google, the website, and type in UAV into their search bar, you get back mostly what people have long thought of as in terms of unmanned aircraft, big military assets flying high in the sky that are essentially sophisticated sensor platforms. But the world has changed in the intervening 10 years. For one thing, if you go to Google now relative to, say, 10 years ago, there's an extra thing at the top of the search bar. There's actually a shopping link. And if you type UAV and you click shopping on that link, you actually get a very different picture of UAVs. Much smaller things, very friendly, a lot of toys. And the world has changed in a substantial way in terms of how the public and the general public thinks about UAVs. Is that there's a lot of interest now in this new technology, in quadrotors, et cetera, and what they can do. And the first thing to ask the question is, well, okay, that's a pretty big change that I can now go to Amazon or a bunch of other websites and buy myself my own personal UAV. What has changed? Well, one thing that has changed is we now have several generations of low-cost, high-power microelectronics. And that industry that's driven changes in lots of places, cell phones and automotive technology as well as UAVs, has had a tremendous impact on these aircraft. Second thing that's changed is low-cost, high-power computation. When I started grad school many, many years ago, the amount of computation that was on the surface of the Earth was about 10 to the 15 flops. It doesn't really matter what a flop is, but 10 to the 15 flops was what all of humanity had in terms of computers, and 10 to the 16 is what's inside everybody's head. So the total amount of computation on Earth at one point was 1/10 of what's inside a person's head. That's absolutely not the case anymore. You can put an enormous amount of computation in very small form factors, including all of us carrying around an enormous amount of computation, and this has been hugely enabling for UAVs. The last thing that's actually had also a remarkable impact is low-cost, high-energy density batteries. That the amount of power that we can now carry around in our computers and our phones, we can put commensurately more into our UAVs. And this has also enabled these new generation of tiny little vehicles. So how did I end up working in UAVs? So interestingly enough, I actually came from an education background in ground robots. I'd done a lot of work in healthcare robotics and service robots, et cetera. I got hired by MIT because MIT saw the coming changes in aircraft driven by the things I just talked about, batteries, power supplies, computers, microelectronics, et cetera, and hired me to bring a lot of the work that ground robots has been developing in terms of autonomy for robots and put it in the air. And so for 10 years, I spent a lot of time with my students building small aircraft that could fly around and use onboard sensors and onboard computation, onboard autonomy to do intelligent things. For instance, this is a little video from my research group a few years ago with a onboard sensor being used to actually sense the environment and build a map. And you can see the UAV flying around. I'm not going to talk that much about the actual sensor used to do this, but you can see that the vehicle is building a very nice floor plan of a building at MIT. That particular floor plan looks a little bit funny because the building is actually a little bit funny. When you see this video here of more rectilinear corridors, you get a better sense of the kind of structure that we can do. So this was an early result in onboard autonomy for UAVs. And a lot of what I'm going to talk about today is the necessary autonomy to actually drive the next generation of UAVs, how the research going on in labs like mine and others around the world, it's not just me, is really going to enable a new generation of consumer and commercial UAVs. That's a very simple demonstration. And perhaps a more compelling demonstration is a result from 2012, where I and two of my students put onboard sensors on board this fixed-wing vehicle and flew it around in this parking garage at MIT. And this was, to our way of thinking, a particularly compelling result, because this is the kind of thing that actually a human pilot with a joystick flying the vehicle around couldn't do. It's not that this is a hard pattern to fly, and it's not that this is a hard vehicle to control. But in this parking garage, there's no place where a human can stand and actually see the aircraft during the entire trajectory. There's no place where a single human actually has enough awareness of what's happening to be able to actually control the vehicle. So you have to have the vehicle do itself. You have to have the vehicle use onboard sensors and onboard autonomy to know where it is, to avoid collisions, and sort of execute the trajectory that you want. So in 2012, we'd done this result, and I was contacted by a friend of mine, Sebastian Thrun, who started Google X. And Google X was this new research entity at Google, focusing on interesting questions. A lot of people think about Google X as like the research arm of Google, and it is a research entity, but it's not the research arm. There is, in fact, a proper research part of Google, which looks at technical questions associated to Google's main business. Things like how to do search better, image retrieval, automatic translation, et cetera, et cetera. That happens inside Google Research. What Google X does is it looks at hard technical questions that are not related to the core business, but that might dramatically disrupt or dramatically solve a bigger problem for the greater world. And they focus really hard on this idea of a moonshot, which is, a technology that will solve some big problem for general society. So perhaps the best known example of Google moonshots is the self-driving car. So what's the big problem with ground transportation right now? It's kind of inefficient. It's really time-consuming, especially in Sao Paulo, if I may. And it's also very dangerous. In the US, 30,000 people lose their lives each year in automobile accidents. So what's the moonshot? Well, how are you going to? The moonshot is to drive down the cost of transportation, drive down the effects of the numbers of deaths, et cetera, by making the cars self-driving. So Google contacted me because they wanted to look at whether or not there was a moonshot that could be brought to bear in small UAVs. Is there some dramatic way that we could change how people live their everyday lives by developing UAV technology? And I'm not going to spend a lot of time talking about this today, but just a few quick facts and figures, because we know that both Amazon, Google, and lots of other people have been talking about building large fleets of UAVs for delivery and all kinds of other things. By far, probably the biggest application of UAV technology in the near term that's really realizable is remote sensing. And remote sensing is for things like infrastructure inspection, imaging bridges, wind turbines, et cetera, agricultural imaging, et cetera. Large numbers of dollars are available here for people who can get reliable systems to do this. Precision agriculture is actually a category by itself, not just imaging, but also very precise delivery of fertilizer and other things. In the US alone, the precision agriculture market from UAVs is predicted to be $9 billion 10 years from now. So again, these are big dollars. Same-day e-commerce, harder to say. $4 billion is still a lot of money. Other applications, specifically of delivery drones, very difficult to get hard numbers. Urgent documents, the governments in the UAE and Dubai have talked about using UAVs for urgent documents, and they believe that there's a significant market there, but it's very difficult to get a hard number. And same thing with food delivery. A lot of interest in this, a lot of interesting prototype demonstrations, but no real notion of how big the market might be. There is also one other potential target, and this is actually something that we thought we might tackle for a long time in terms of moonshot, which is forget about business applications and actually think about healthcare. Out-of-hospital emergency healthcare has a very strong need for intervention, specifically in the context of cardiac arrest. And so there is a real potential for out-of-hospital urgent care delivery by UAV having a significant impact, again, on how many people lose their lives, for instance, due to cardiac arrest. Just to give you an example of how big that, what that looks like, the governments around the world, and I apologize, I don't know whether Brazil does this, but certainly in the US and in Great Britain, they will give local and state governments money to go and buy defibrillators and put them in public locations so that they're readily available quickly before the ambulance or fire truck arrives. But this is a really hard thing to do at scale. So for instance, the government of Great Britain gave the Isle of Man money to go and buy public access defibrillators, and these are the 9 that the Isle of Man bought and put up in remote locations like you can see on the right here, which is, for an island of 80,000 people, it's not really the best way to actually go and get defibrillators into people's hands. But this healthcare application has a number of challenges, and so I advertise it not as a solved problem right now or something that people should go and do, but as a really great potential moonshot with strong humanitarian implications. What Google ended up wanting to do, and what we spent we spent 2 years, from 2012 to 2014 doing, is building a delivery system that makes UAV delivery available to the average person. We know that there's a tremendous friction right now in how things move around the world. We used to move things around the world. Ground transportation used to be done on water, and that was many hundreds of years ago, and that's to a large extent why cities were built on rivers. And then we invented the railway, and the railroad allowed us to put cities wherever we wanted, do long-distance transportation without needing waterways, and that, for instance, opened up the US and Canada across the West. Then, obviously, automobile transportation had a tremendous impact in being able to go in lots and lots of places, and the highway interstate infrastructure in the US especially revolutionized manufacturing and enabled just-in-time manufacturing. And now, air transportation makes somewhat ridiculous things possible. I can take an electronic drawing of a component and email it to a vendor in Hong Kong and have that vendor fabricate a prototype for me and FedEx it back the next day. So I can get 24-hour turnaround in terms of just-in-time prototyping on the other side of the earth from at least Boston. But as I said, there's a little bit of friction in there still, because FedEx, as great as it is, will deliver that part using great big airplanes to get it from Hong Kong to Boston, where I live, and then it sits in a FedEx distribution center for 6 hours. I can pull out my phone and get a 2-hour window where I might get it delivered, but I can't pull out my phone and say, I'm at work, I know you've got it, I want it in the next 10 minutes. And so that's really where the speed and the sort of the ubiquity of UAVs really can have an impact. And that's the promise of the Project Wing system that we spent 2 years setting up. And I just want to show you a video of the results at the end of 2 years.
Throughout history, there have been a series of innovations that have each taken a huge chunk out of the friction of moving things around. Project Wing aspires to take another big chunk of the remaining friction out of moving things around the world. In Australia, the goal of being here is to show that the hard work over the last few years has resulted in a reliable system that can do autonomous delivery. And we also really just want to get out and learn what it's like to actually deliver to the neighbor meal and see what it's like from their perspective. Years from a product, but it is sort of the first prototype that we want to stand behind. The next phase is to take the momentum and the enthusiasm that was built internally and not drive it towards enabling the dream of delivering stuff more quickly. With proper and due safety, working together, we can get to this future, I think, surprisingly.
So that's where we got to in 2014. Why did Google ask me to help start this project? Because as an academic, I have a lot of experience in investigating different technologies and building prototypes. That's what academics largely do, is build prototypes and demonstrate what could be possible. I'm very happy to be back at MIT now because I want to think about what the next technology challenges are in this space and turn the team over to Dave Voss, who you saw at the end of the video there, who's going to take the system and turn it into a real product. And that's really where somebody with experience in industry and turning things into real products really is the right person to lead the team. So what I want to do for the remainder of this talk is actually talk to you about what the technology challenges were that we identified and hypothesized what some of the solutions might be. And then also what some of the technology challenges are that are massively unsolved right now, and where I think academia and industry could really work well together in order to enable much more sophisticated UAVs than what are currently available as actual products. Again, I want to emphasize very much that was a prototype, but it was a good enough prototype and a good enough demonstration of what might happen that Google was willing to double down, continue building the team, and bring in an actual product development specialist. So in the space of delivery, what are some of the technology challenges, especially urban delivery? Well, the first challenge is the urban environment itself. How do you actually get a vehicle that can take off in a city like Sao Paulo and fly relatively high speed across the city, come to a stop, and then get a package down to the ground, and then head back home? This is not something, that combinations of things is not something that air vehicles are really good at. We have lots of examples of multi-rotorcraft, conventional helicopters, rotary wing vehicles that are going to be just fine at going up and down and stopping in the urban environment, but they don't go very quickly. Most of the quadrotors that you can buy from Hobby Lobby and wherever have a top speed of about 7 to 10 miles per hour, which is fine for hobbyist applications, but if you're paying a premium for your package to be delivered across town, then it better be as fast as you can do it. In contrast, fixed-wing aircraft go fast. They're great for going across urban environments. They're a big part of why we can do this just-in-time prototyping from Hong Kong to Boston and back. But up and down in the urban environment, not going to be able to put runways in the middle of Sao Paulo. And coming to a halt and delivering things is, again, a challenge for fixed-wing vehicles. Now, normally I move on to hybrid vehicles at this point, but I actually want to show a video, and I'm really happy to be able to show this video here, because there is actually an example of somebody doing deliveries from a fixed-wing aircraft in Brazil. So a guy called Nate Saint in the 50s would use his fixed-wing aircraft, I think it was a Beechcraft, what he would do is he would put whatever he wanted to deliver to the indigenous people in the Amazon basin. He would deliver supplies and medicine, et cetera, from a bucket hanging from the back of his plane. And he could actually position the bucket precisely by doing big, big circles, and like you see there. And then, once somebody comes out and gets the thing out of the bucket, then the plane gains altitude and pulls the bucket off the ground and goes on back home. And so I just want to, it's kind of fun to show this video here, because in Brazil, in the 50s, people really were doing, not unmanned airborne delivery, manned airborne delivery, but fixed wing in a very interesting way. And so I think this is really cool. This video is obviously not from the 50s. This is his son, Steve Saint, demonstrating his father's technology in 1998, I think. But it's nice to have a video of somebody doing this. Unfortunately, in the urban environment, this kind of technology, long lines and buckets, probably not realistic. So we abandoned this concept relatively quickly, and we thought hard about hybrid vehicles, vehicles that are a mixture of VTOL and also fixed-wing flight. Unfortunately, hybrid aircraft have a terrible reputation in the vehicle design community. And there's this famous paper written about 10 years ago about all the different ways that hybrid aircraft are actually not really useful. And the ground, in some cases, is literally littered with the remains of these aircraft that never actually got themselves off the ground. Some of these do work on our viable aircraft. You may recognize the Harrier jump jet in the bottom left, and you may recognize the V-22 Osprey on the far right, which is an aircraft used by the US Marines. And then on the top left, there's the Joint Strike Fighter, which is the next generation of jet that the U.S., all three armed forces are planning to start using in the next few years. And it is capable of very short vertical takeoff as well as fast forward flight. All of these aircraft, again, like I say, have very bad reputations because going from vertical up-down to fast forward flight is a dangerous activity, and a lot of the time the vehicles become unstable. But with modern computational techniques, modern sensors, modern electronics, there is an opportunity to go back and revisit some of these aircraft designs and see how appropriate they might be for certainly small-scale operations and small-scale UAVs in the urban environment. All of these here, we ended up not choosing as our first one, and I know that Google has said that they're continuing to explore the vehicle design space. The vehicle that we went with first is shown here as a tail-sitter. So the idea is that in vertical orientation, it's got enough propulsion that it can hover, but it can also pitch forward and go into forward flight. And you saw that happening in the video, and I'll show another video. No, I won't show. You've seen that video already. These vehicles do exist. We weren't the only ones who have built a tail sitter, and that was because we knew that there was at least some active development around tail sitter technology. We thought that would be a good form factor to actually start with. But as I say, there's lots and lots of room for other vehicles of this type to be studied and possibly applied in these kinds of domains. My research group is continuing to actually look at other vehicle types back at MIT. Another research challenge is, how do you get the package down to the ground? So even if you have a tail sitter that's capable of taking off in vertical, pitching forward into forward flight, and then coming to a halt over your house, carrying whatever it is you've ordered from Amazon or whoever, how do you get the package down to the ground? You could just drop it, put in enough padding, and hope for the best. We did try that, actually, and that turns out, for obvious reasons, to be a terrible idea. The user experience of the person on the ground is less than optimal. What I thought was the right answer was to actually have the vehicle land with the package in the vehicle fuselage. And you kind of get a flavor of that from Amazon's demonstration of this kind of thing, where the Amazon quad rotor or hex rotor comes down and lands outside the person's glass door. The problem with landing the vehicle is also the user experience as they're getting their package is not great. You can imagine that you've paid a premium for whatever you've ordered from Amazon, your USB cable or your infant formula ibuprofen from the local pharmacy. And because you paid a premium, you want it fast, you're not interested in waiting for the vehicle to come all the way down to the ground and actually turn its rotors off. Our experiments with this showed that it's very difficult to get people to stop actually reaching up for their package. And the problem is, if the package is inside the vehicle, that's where the propellers are, or the whirling blades of death. And so we recognized that was actually not a viable strategy for getting the package down to the ground. And so, again, you saw in the video that the winch solution, where the package comes down in a controlled manner, but still separated from the vehicle, which is up high and out of harm's way. And then there's a little package of electronics at the bottom with the delivery package that is doing situation assessment, looking to see what's going on around, noticing when the package is on the ground, and then gets hauled back up once the package is delivered. Another challenge, of course, is then if you've got this long line with the package at the end of it, the urban environment is full of stuff to actually get in the way, trees and so on, buildings. How is the vehicle actually going to know where to put the package? This is actually kind of an easier problem than we thought, because the quality of 3D map data that's available through Google and other entities is actually relatively high. So in places where there aren't a lot of trees, like you see on the left, this is the Bay Area of California, you could see that there aren't a lot of things in the way, and Google and others have highly accurate maps. So you know where the trees are, and you know where other things are, and so the vehicle onboard autonomy can plan to avoid these kinds of obstacles. On the right, you see a harder situation with trees. that really obscure any reasonable delivery point. And so this is a problem that's going to have to be solved for all of these delivery technologies, is how do you actually do delivery to somebody's house when they're covered in trees? And it might be the case that not everybody's house is actually going to be available for the UAV delivery service. But the real problem, of course, is that not everything actually exists in the map. So this is an image from Dublin in Ireland. I know that places like this exist in Boston. I would surmise that Sao Paulo has power lines that look like this, and these don't show up in any of the existing map databases right now. So the vehicle's onboard sensors would have to be able to detect these and make appropriate adjustments as the package comes down to the ground. And that's a huge unsolved problem. And to a certain extent, this kind of need for sensing and onboard autonomy is prevalent all the way through all of the issues that these UAV systems are facing. And so with my remaining time, what I actually want to do is talk about I talked a little bit about what some of the opportunities are, and I talked about what some of the technologies that we looked at in the course of the 2 years doing Project Wing. But what are the real challenges that still lie out there for a real commercial UAV system? So one of the first challenges is, unfortunately, as good as the power supplies are for these vehicles, as good as the battery technology is, it's not good enough. Gram for gram, there is no better fuel in terms of both energy density and power density than carbon-based fuels, gasoline, diesel, etc. The problem with gasoline and diesel engines, of course, is, first of all, this is a very environmentally unfriendly technology. We'd love to get away from carbon-based fuels as quickly as possible. The last thing we want to do is start filling the skies with a bunch of internal combustion engines. And the other thing is that for airplanes, they are a source of failure. That an electric propulsion system is, for various reasons, more reliable than gasoline and diesel, but it's just not anywhere near as good in terms of the mass you have to carry in order to carry enough power. And this just is not getting better fast enough. I'm not a battery technology expert, so all I can do is complain. But this is it, and it's not just the energy density, it's also these batteries are very hard on the environment to make, and we chew through batteries on UAVs really, really quickly. So you're using a lot of precious metals in these batteries, and you're using a lot of batteries in order to run these systems. So it's a problem. I made mention of safety and reliability in talking about internal combustion engines. Safety and reliability is a huge problem for the UAVs that we can buy from the web, et cetera, right now. How many people recognize this picture? Hands up. So 2 or 3 or 4 or 5. So small number of you recognize this picture. For those of you who don't recognize this picture, this is a DJI Phantom. Costs about $1,200 from the manufacturer, from resellers. And this picture was taken by the US Secret Service on the lawn of the White House. This is a bad place to crash your UAV. Happily, all's well that ended well. This was, the pilot admitted there was beer involved. Which explains the state of the aircraft. But it can't be the case that these aircraft can come down on the lawn of the White House. They have to be smarter, and they're not right now. We know that this is not just an isolated incident. You can actually go to Facebook and join the psychological support page for everybody who's crashed their DJI aircraft. And I'm being a little bit hard on DJI. Part of the reason why they have such a large volume of crashes is because they are the biggest UAV manufacturer in the world. They sell on the order of 100,000 vehicles per month. That's an enormous number of UAVs. Their anticipated evaluation is a $10 billion company, so hugely successful. The reason they crash so much is just because there's a lot of them. But at the same time, you don't see 100,000 vehicles per month sales translating into 100,000 new vehicles in the sky per month. So I tried to figure out where these vehicles are, and it seems to be that a lot of them end up either at the bottom of a lake or in the back of a closet in relatively short order. So the lack of reliability, I guess, creates a real business model for DJI, but it's not sustainable. But it's not just DJI. I'm being unfair to DJI. Yamaha has an enormous success story in terms of UAVs. the figures, this is an article from Precision Agriculture in 2013, observed that 40% of Japanese rice paddies are fertilized by UAVs. So that sounds enormous. 40% of Japanese rice paddies is a huge amount. Until you actually dig into the numbers and actually find out that that actually converts to 2,000 helicopters. So, okay, 40% is a lot of agriculture that you're providing service to, but you're doing it with a very small number of the same aircraft. So this is not a $10 billion industry. This is barely a $10 million industry in Japan, even though the figures are somewhat astonishing. And oh, by the way, you can't buy a Yamaha RMAX. Yamaha will not sell one to you. They will only lease one to you with a pilot agreement where they provide the pilot. And the reason is because in 2009, unfortunately, a Precision Agriculture Yamaha RMAX crashed in South Korea and killed a farm worker. So the reliability, even in these success stories, is not where you'd like it to be. And this really highlights, actually, oh, hang on a second, one more just quick fact. There are successful commercial UAV systems in addition to Yamaha RMAX that have very high reliability ratings. DHL in Germany started a delivery service to the Isle of Juist using a microdrones quadrotor helicopter. And microdrones has an enormously good track record in terms of safety. They take safety and reliability very, very seriously. But the way they do that is by having very strong bespoke engineering that involves a huge amount of manpower in terms of very reliable manufacturing. They hand wrap the windings on their motors. It's not really clear what that means, but if you think about an electric motor, you know there's a bunch of wire inside there. And if you've got a person actually wrapping the wires inside there, this is not scalable. You're not going to sell 100,000 vehicles per month if you're hand wrapping your motors in order to get that kind of reliability. So there's a mismatch between where the technology is right now and where it needs to get to in order to really grow a commercial system that's reliable and safe at this kind of scale. The other, so that bespoke engineering involves a huge amount of human labor. And that human labor shows up in other places in terms of current UAV operating models as well. The military, we know, has a lot of UAVs, and their biggest complaint is actually the operator cost. That unmanned systems have a greater manpower cost than manned systems, which sounds crazy. But the point of fact is that you need typically 2 people per 1 UAV. And that's, of course, completely unsustainable for a commercial delivery service or a commercial precision agriculture service. You need to be able to, a large extent, launch and forget and have the onboard autonomy take care of all these things with maybe just a little bit of human intervention just to clarify mission specifications or something like that. And so what that really does is it puts the emphasis on the autonomy. And this is where I'm really excited about the opportunities for academics like myself to have impact. Autonomy is really transforming the ground transportation. This is an image of the MIT self-driving car. We know that the Google self-driving car efforts and Nissan and Ford and Toyota, et cetera, are built on the basis of the technology that's been developed at labs like MIT and Stanford and Carnegie Mellon. Something else that's really revolutionized autonomy, of course, the thing that's really giving me hope is not just the presence of the computation that I talked about earlier, but also the sensors that we can get now. The sensors are, so this is the bottom right corner is a laser rangefinder. And what it does is it basically tells you the distance to the nearest obstacle with very, very high accuracy and precision. And these kinds of laser rangefinders are absolutely what enabled modern ground robots in terms of navigation, and absolutely enabled a lot of the work from my lab that I showed at the beginning of this talk in terms of the quadrotor building maps of the environment and the aircraft flying through the parking garage. Now, unfortunately, these kinds of sensors, as great as they are for self-driving cars, et cetera, are expensive. But what is exciting right now is that the technology is maturing where you can do this kind of estimation of where the vehicle is without GPS and estimating what the environmental structure is around the aircraft without a laser. You can actually do it with just a basic camera. And this is a video, again from my group, showing a quadrotor flying in the same environment that I showed at the beginning of the talk, but it's no longer carrying a $5,000 laser rangefinder. It's carrying a $5 camera, plus a really good computer. So don't get me wrong. There's cost of things in there, but the computers are generally in the order of $400 or $500, which $500 computer plus a $5 camera is a lot cheaper than a $100 computer and a $5,000 laser rangefinder. And so this kind of camera-based navigation, I think, is going to be a game changer for these kinds of vehicles in terms of driving up the autonomy. Another major problem is the so-called detect and avoid problem. So, okay, we have cameras or laser rangefinders that can help the vehicles deal with the absence of GPS, know where they are in the world, detect obstacles and not let them fly around. But that's fine in indoor environments or sort of ground structure. What about other aircraft? How do you see other aircraft and not hit them? And lots of people say for the small kinds of UAVs, doing delivery in the urban environment, doing photography, remote sensing, there are no other aircraft to hit, so you don't have to worry about the detect and avoid problem. That's true right now, but not for nothing. There are 2 drone-based delivery companies that have real development test programs going on right now, Google and Amazon, and they're going to fill the same skies. And so maybe the Project Wing vehicle doesn't have to worry about not hitting a Cessna, because the Project Wing vehicle is flying at 100 feet above ground and there's no Cessnas there. But it is going to have to worry about the prime air vehicle. And so there needs to be some way for these unmanned aircraft to deconflict themselves. This has been, for those of you who have followed the UAV industry in the last couple of years, know that this is actually one of the biggest bottlenecks in at least the US to getting UAVs regulated for safe operation. Because UAVs are so, frankly, dumb right now, they can't see other aircraft, they can't see other RC aircraft, they can't see other UAVs, they can't see other manned aircraft, and so at some point, some UAV is going to fly into the path of an oncoming Cessna and have a collision, and it's going to be bad. So right now, the way the US at least regulates that is by making sure that a human pilot can always see the airspace at all times. This actually, when I look at the technology, this is getting better quickly. So short term, this is obviously a military-grade ground radar. There aren't actual non-military-grade radars available, but they're coming. And so you can imagine ground radar talking to the air vehicle, doing deconfliction. In the short term, very viable. And then longer term, there are actual labs. So this is a picture taken from Kamal Sarabandi's lab at the University of Michigan. And he's developing lightweight, small, low-power airborne radar systems that could very well go into small quadrotor UAVs and give them the awareness they need to not hit things. Another problem is, of course, just managing the traffic. So it's not enough just to not hit these things. You really do want a proper air transportation system for UAVs that allows the UAVs to integrate with each other, that allows them to integrate with manned aircraft. There's a system in place, air traffic control system, for regulating manned aircraft. If a manned aircraft can't take off right now because it's too dangerous, ATC will tell them. We need a way to do that for unmanned aircraft too. NASA in the US is looking at this, and I think there's a huge opportunity for, again, academia and industry to work together to solve this very hard problem. I'm not going to spend a lot of time on this, but I like putting this up because it's actually something that I really enjoy talking about right now, which is that the environment in the urban environment, the atmospheric environment in the urban city is actually really, really complicated. I have a new appreciation for just how complicated the wind patterns are in the urban environments. That I did not know that buildings shed vortices, just like a wing sheds a vortex as wind goes by it. And this is a useful thing for small UAV to know, because you wouldn't want to do delivery in the middle of a hostile wind pattern. You'd actually want to understand the wind pattern and do the deliveries in the right place relative to the wind. I'll skip over that. One very last thing that I don't have much to say on, but people do like to ask about are 2 things, are noise and privacy. Most commercial UAVs right now are extremely noisy. You could really hear them, and it's very unlikely that we'd be willing to put up with our neighbor, calling a UAV to do delivery over their house at like 1 o'clock in the morning and waking up the whole neighborhood. And there's no question this is a problem right now, but actually we do know how to make quiet UAVs. It's just that nobody's doing so. And so this problem will get solved as the need for the quiet actually goes up. There are efficiency issues related to making the vehicles quiet, but it'll get solved. And the other one, of course, is privacy. Civilian drones, people are talking about the government using them to spy on people. I don't have a lot to say here because it's such a personal issue, and it varies very much from country to country. In the US, we have no strong privacy regulation body. In Brazil, I believe you do, and there are rules. And in some places like Australia, we discovered that actually they're very comfortable with the idea of UAVs collecting images, so long as everybody knows what's happening. And so there's no blanket solution to this. Each community and each country and each state is going to have to make up their own mind how to solve that. So just to conclude, people often ask me, is this technology real? Are we really going to have UAVs flying around over our cities in the near future? And the answer is yes. I think this is going to happen. These problems are going to get solved. But there are three big total cost of ownership problems. Number one is we've got to drive down the operator costs. The second is we've got to drive down the battery costs. And the third is we've got to drive down or drive up the quality of the back-end infrastructure and drive down those costs in order to increase safety and reliability. And then autonomy is going to be key to all three of these technology challenges. So I'll stop there and say thank you very much.